11th lecture of MAT-601, that is Real Analysis 2. So, in this lecture, we'll start chapter 4, that is Calculus. So, in the chapter, we will see, so that is 4.1 sets of measure 0. So, then definition of Riemann integral, then, yeah, existence of Riemann integral, fundamental theorem of calculus. So, this is the outline of this chapter. So let's continue first topic, that is 4.1 sets of measure 0. So there is a definition of set of measure 0. The subset capital E of R1. So what is R1 here? So R1, that is set of real numbers. It is matrix space. Real numbers with absolute metric is said to be measure 0 if for each epsilon is greater than 0 there exists finite or countable number of open intervals I1, I2 up to it goes to infinity, says that. So that set E should be contained in union of all these intervals, countable number of intervals, and sum of length of all these intervals should be still less than epsilon. It should be true for each epsilon is greater than 0. So in that case, we say that so E is of measure 0. So let us see what is set of measure 0. Suppose E is subset of real numbers. So when we say E is of measure 0, so for this E, so for given epsilon is greater than 0, for each epsilon is greater than 0, there should exist countable number of intervals. So these intervals should satisfy following two conditions. First, their union should contain set E, and sum of length of all these intervals should be still less than epsilon. So this is the definition of set of measure 0. Next, so there is one theorem, that is if each of the subsets E1, E2 up to it goes to infinity. So these are countable number of subsets of R1. So each set is of measure 0, then their union, so countable union of this sets of measure 0 is also of measure 0. Means if E1 is of measure 0, E2 is of measure 0 up to, so capital E to suffix En, and it goes to infinity. All the sets are of measure 0, then their union. So this is countable union of all these sets. Then their countable union is also of measure 0. So to prove this theorem, so in short you can write that is countable union of sets of measure 0 is again countable. So in short you can write this statement, that is countable union of sets of measure 0 is again of measure 0. So you can write this statement in short. So we'll prove this. So to use definition of set of measure 0, let us fix epsilon, one epsilon which is greater than 0. Since epsilon n means for each n, epsilon n has measure 0. So it is true for each n belongs to n, that is set of natural numbers. So there exists finite or countable number of open intervals which cover capital N and whose lengths add up to less than epsilon divided by 2 raised to n. So if you take suppose n equal to 1, then what happens? Epsilon 1 is set of measure 0. So for epsilon 1, there exists countable number of intervals I1, I2 up to it goes to. So for for E1, so I can write I1 and suffix, I1 suffix, and I'm here writing its height is 1. So I1 1, then I2 1, then I3 1. It goes to infinity. So these are the countable number of intervals, and which satisfy definition of set of measure 0 means their union covers E1 and their length of the sum is strict less than epsilon. So here, so I'm taking n equal to 1. So here their sum, length of sum will be, that is I, you can take I 1, and I varies from here 1 to infinity, and it is strict less than epsilon divided by 2. So this is true for epsilon 1. So naturally, so already we have fixed epsilon. So since epsilon e1 is countable, sorry, set of measure 0, so you will get so countable number of such intervals. Similarly for epsilon 2, so if you take n equal to 2, so you will get another collection of intervals. So you can take suppose I1 2, then I2 2, then I3 2, it goes to infinity, and their union covers epsilon to E2, sorry, and summation, that is I2. So here I varies from 1 to infinity is less than epsilon divided by 2 square. So likewise, so it is true for epsilon n. So if we collect, if we take union of all such intervals, that is I11, I21, I31 goes to infinity, I12, I22, I32, it goes to infinity, and likewise. So if we take union of all these intervals, then that union covers union of En. The union of all such open intervals for all n belongs to n then covers, so this union of n varies from 1 to infinity, and length of all these intervals, which are countably many, add up to. So if you add their lengths, then we'll get, see, so epsilon divided by 2 plus epsilon divided by 2 square plus up to, you can write here if epsilon divided by 2 raised to n plus it goes to infinity. So epsilon divided by 2 you can take common, so in bracket it will be 1 plus half square plus half cube plus goes to infinity, and which is geometric series. So you'll get, so this quantity is nothing but 1 minus half, so it will be epsilon divided by 2 into 1 minus half, and that is half, what is this, yeah, so what is the value of this? There is 1 upon 1 minus half. So this half will be at numerator, and you will get epsilon by 2 into 2, and that is equal to epsilon. So naturally their length will be less than epsilon, and their, so union of all these intervals covers union of En, and therefore this countable union of En varies from 1 to infinity will be of measure 0. So this is straightforward application of definition. So next, so there is one phrase that is almost everywhere. So what is the meaning of almost everywhere? In short, it can be written as A dot E dot. Likewise, so it is phrase, we use this phrase in existence of Riemann integration. So what is the meaning of almost everywhere? A statement is said to hold at almost every point of closed interval AB, or almost everywhere in the closed interval AB, if the set of points of AB at which the statement does not hold is of measure 0. That is, suppose if you consider f is continuous function on closed interval AB, and if E is the set of discontinuous points of f in the closed interval AB, then the measure of E should be 0. So in that case, we can say that f is almost everywhere continuous on the closed interval AB. Means in that interval, the statement, the points at which this statement does not hold, that is, set of that point should have measure 0. So remark we can write f is continuous at almost every point of AB, means the same as if E is the set of points of AB at which the f is not continuous, then E is of measure 0. So this is about the phrase almost everywhere. So next, definition of Riemann integral. So before starting definition of Riemann, or before defining Riemann integral, so in that we will first define Riemann integral, upper Riemann integral, lower Riemann integral, and total Riemann integral. So before that, we'll see some basic definitions. So let's suppose IB. So this is the definition of maximum and minimum of function on interval. So you can write. So these are the definitions of maxima and minima of function on the interval. So what is meaning of capital M F I? So it is maximum of function f on the closed interval I. So let's suppose I be any bounded interval of real numbers and let f be bounded function on closed interval I. So we define maximum of f on I. It is nothing but least upper bound of fx in that interval I. So for x belongs to I, the least upper bound of fx means values of that function. And what is minimum of f on I? So greatest lower bound of fx in the interval I. So these are the basic definitions. So next definition, that is subdivision of an interval. It is also called partition of an interval. Subdivision of interval or partition of interval. So let's suppose I, it is closed bound interval AB. So be any interval of R1, a finite subset capital Phi, which contains suppose n plus 1 points x0 x1 up to xn, is said to be a subdivision of closed and bounded interval AB if it satisfies following condition. First, so a should be equal to x0, and second, xn should be equal to b, means first point of this set should be equal to a and last point of this set should be equal to b, and internal points means x1 x2 up to xn minus 1 should satisfy this relation, that is x1 should be still greater than x0, x2 should be still greater than x1, likewise. So in that case, this set P is called subdivision of this closed interval AB. So geometrically we can observe, suppose P is a set which contains suppose x0 x1 x2 up to xm. So these n plus 1 points, and suppose closed interval AB is one closed bounded interval. So here a equal to x0, then x1 x2 x3, it goes to xn minus 2 xn minus 1 and xn is equal to b. So here this set P divides this closed interval AB in n equal parts. So this set P divides I in n equal parts. So these n equal parts are called subintervals, and these are given by, so you can write I1 as x0 x1, I2 as x1 x2, I3 as x3 x4, and likewise In as xn minus 1 to xn. So these intervals I1, I2 up to In are called subintervals or component intervals of this closed and bounded interval I with respect to this subdivision P or partition P. So this is definition of subdivision. So subdivision of an interval is also called partition of an interval. So next definition, that is refinement of subdivision. So we say that suppose tau is a refinement of sigma if sigma is subset of tau. Means if we add at least one point in the original subdivision, then resulting subdivision will be the refinement of original subdivision. So refinement 2 is often from subdivision 2 by adding some extra points. So here, suppose sigma is subdivision which contains suppose x0, x1, x2 up to xn, means n plus 1 points, and suppose 2, it is a refinement. So how it will be the refinement of original subdivision? So you can add at least one point in original subdivision. So I'm adding xk star between xk minus 1 and suppose xk. So resulting subdivision, I'm writing x0, x1, x2, it goes to suppose xk minus 1, and I'm adding one single point between xk minus 1 and xk. So it is suppose xk star and then xk, and it goes to xn. So tau contains suppose n plus 2 points, sigma contains n plus 1 point. So here So sigma is a subset of tau, and tau contains more points than sigma. So tau will be the refinement of sigma. So this is the definition of refinement. So next definition of upper sum. So let f be a bounded function on the closed bounded interval AB, and sigma be any subdivision of closed interval AB. So we define upper sum of f with respect to sigma. So this is notation for upper sum of f with respect to sigma. So it is called the upper sum for f corresponding to subdivision sigma as. So definition. So upper sum of f with respect to sigma is nothing but summation k varies from 1 to n, maximum of function f on ik into length of ik. So if we write this summation term wise, so what is first term? So for k equal to 1, so you can write, see, so here we are putting k equal to 1, then k equal to 2, then k equal to n. So for k equal to 1, so it will be maximum of function f on I1 into length of I1. For k equal to 2, so that is second term in this summation, it will be maximum of function f on I2 into length of I2 plus up to 2, plus it will be maximum of f on I1 in into length of in. So it is a summation of n terms. So this sum is called upper sum. And why it is called upper? Because in each term there is maximum of that function on corresponding interval. So it is summation of n terms. So this summation is called upper sum of f with respect to subdivision sigma. So here I1, I2 up to in are the component intervals of subdivision sigma. So this is the definition of upper sum. So likewise, we can define lower sum. So let f be a bounded function on closed and bounded interval AB, and let sigma be any subdivision of closed interval AB. So we define the lower sum of f with respect to sigma. So it is called the lower sum for f corresponding to sigma as. So this is notation for lower sum, and it is again summation of n terms, but in each term, so there is minimum value instead of maximum, there is minimum. Everything is same. So like upper sum, so summation k varies from 1 to n, minimum of f on ik into length of ik. So if you take k equal to 1, so you'll get first term in the summation. So it will be minimum of f on I1 into length of I1 plus minimum of f into I2 into length of I2 plus goes to infinity. Not goes to infinity, it goes to n. So what is last term in minimum of f on in into length of in. So obviously it can be observed that so lower sum of f with respect to subdivision sigma will be always less than equal to upper sum, because in lower sum there is minimum value and in upper sum there is maximum value. So naturally lower sum will be less than equal to upper sum. So this relation is always true. So subdivision should be same. So here is sigma, here is sigma. If we change subdivision, then we should do this result. So this is definition of lower sum and upper sum. So geometrical interpretation of upper sum and lower sum is there. So we'll continue this in next lecture. So let's stop here.